All right, we're going on to a new topic now, and the new topic is beam deflection, which we have been alluding to all semester, pretty much from the beginning. And we have so in a sense, we're getting back to beams, as we've been covering. Let's just take this very simple situation. I've got a beam here with a point load on it, and then when that beam deflects, it's going to create a shape like that. And we want the equation of that line. And we have our coordinate system, x and y. If I eliminate so I'm going to eliminate the beam from the picture, just to give you an understanding, what are we going to get? We're going to get this shape here is going to look like that. And if we extended it, it would look something like that. And so this is a pure, simple math problem in a way. We want the equation of this, and maybe that's a parabola, maybe it's third order or fourth order, but it's some sort of polynomial in the way that for the loading that we're going to do. So we just want the equation of this polynomial here. That's our goal. We have already talked about the basic relationship, and that was that the second derivative of y with respect to x is equal to 1 over EI times m, where m is what? M is the moment diagram equation. We've already developed the moment diagram equation, and we're simply going to integrate it 2 more times. EI is going to be a constant. That's the bending stiffness. We've talked about that. And if we integrate this equation once, we get dy dx is equal to 1 over EI times the integral of m dx. We integrate it again. We get that y is equal to 1 over EI times the integral of m dx. So notice this gives us the equation of the line. That's y. And this is the derivative of that, which means that gives us the slope of the line. So sometimes what we're going to want to know is, well, we're going to need the slope. So in other words, most typically, the slope here is 0. So when the slope is 0, we are going to get the maximum deflection. So we are going to, for various reasons, that's one of them, going to be interested in also getting the slope, which is simply how do we get the slope? We integrate the moment diagram just once. So we're integrate it once, then we're going to integrate it again, and we're going to be interested in both the first time we integrate it and the second time we integrate it. Now, when we integrate twice to get our y, what does that mean? Well, we're going to get 2 more constants. And we're going to need to use the boundary conditions to get the constants. So we're going to, look at 2 different types of beams, the simply supported beam and the cantilever beam. And we want to look at the boundary conditions for both of those situations. It's very straightforward. We just looked at the simply supported beam. If we have a load that deforms the beam like that, then what do we see? Well, we always have put it this way, we always have our coordinate system the way we've always done it, which is x at the far left and then y going upward. And what do we see? Well, at x equals 0, y equals 0. In other words, for that line there, y equals 0. And then what do we see? Over here, y is also equal to 0. So our next one is at x equals L, y equals 0. We're going to use those two boundary conditions, and those two boundary conditions are going to give us our C's. If we have a cantilever beam, the way that the beam is going to deflect is like this. In other words, it's fixed at this location. We say there is no rotation at that location. In other words, the beam does not, it goes straight out of the wall in a nutshell, which makes sense. It's fixed over here, so the beam goes like that. Now, in other words, it does not do this. Okay, so that is wrong. I only show that for clarity that that is absolutely not what happens. Why does it not happen that way? Because the beam is fixed at the wall and it goes straight out and then it bends down. Once we recognize that this is the shape, what do we learn? We learn that at x equals 0, dy dx equals 0. So in other words, the slope of the line right there is 0. It's straight out from the wall. The other is that at x equals 0, y equals 0. So again, there's no deflection at the wall. So we're going to use these two boundary conditions to solve the cantilever beam. Now, if the cantilever beam is anchored at the other side, then what do we have? Then at x equals L, the slope is 0. So at x equals L, there the slope is 0. And at x equals L, the deflection is 0. So now, just to give you an idea of what happens if I have a problem like this, where I have my load here. Well, if the load is in the middle, just a single point load in the middle of the beam, what happens? Well, we know that the beam bends like this, but in this region, there's no load on the beam, and therefore the beam is straight. So if I want to figure out what is the deflection at this distance, or at the very end of the beam, what do I have to do? Well, what I do is I simply analyze only this portion to start with, and I get the deflection and slope there, and then I extend that straight line just using simple geometry. So we're going to run into something like that. I'm not going to go through these. We're not going to cover these simply because these are statically indeterminate situations. So I'm just going to go forward. Let's look at the easiest way to do these problems is with an example. They're generally very straightforward. Everybody gets them. So these are not very difficult because everybody can integrate a polynomial. So some of it is review. So let's just say that I have this cantilever beam with a load of 100 pounds per inch. EI is given to be 30 times 10 to the 6 pound inches. And my goal is to find the end deflection. So we start out, we have to draw our shear and bending moment diagrams. And the reactions, I'm not going to go through this because we've done it a million times. So I get these are my reactions. And what do? I get my shear diagram, go up 5,000. This total load is 5,000. I go down. Looks like that. We know the slope there is negative 100. And then I get my moment diagram. I have this counterclockwise moment there, so I go down 125. And then I know that area is 125,000, and I get a moment diagram that looks like that. To write the equations, I start with writing, this is my simplest equation to start with, so I write that. I know the slope is negative 100. I know that the intercept is 5,000. So we get that V is equal to minus 100 plus 5,000. I integrate v to get m. So integrating that, I get minus 50x squared plus 5,000x plus what? Plus a c1. I get the c1 by noting that at x equals 0, m is negative 125,000. And I get that c1 is negative 125,000. And that gives me this equation for the moment diagram. And so now I'm going to integrate this 2 more times, and I have to remember I have to put in the constant 1 over EI. So I integrate it once, so dy dx is going to be equal to 1 over EI times the integral of m dx, and it's just a polynomial, so I integrate that polynomial and then I put in the c2. I integrate it again, that polynomial, and what do I end up with? I end up with, at the end, c2x plus c3. So now I have to get the c2 and the c3. How do I get that? Well, I'm going to use my boundary conditions. So one of the boundary conditions is that at x equals 0, dy dx equals 0, because it's a cantilever beam. We just went through it. So I use my dy dx equation, come down here, I set it to 0, and I put in x equals 0, so I get that 0 is equal to 1 over EI, don't forget that, times 0 plus 0 minus 0 plus C2, and I solve for C2, and I get that C2 is 0. I use my other boundary condition, which is at x equals 0, y equals 0. So I use my y equation. I plug that in. And I get 0 is equal to 1 over EI times 0 plus 0 minus 0 plus 0 plus C3. And I get that C3 equals 0. So then my final equation is that y is equal to 1 over EI times, you can see it there. And how do I get the end deflection? Well, the end deflection is straightforward. I just put in x equals 50 to get the end deflection. I plug it in, I get y is equal to negative 2.6 inches, and what does the negative mean? The negative means that it's down, which makes sense because we expect that. We know that this is going like this, and we are in the negative y direction. So y is going to be negative there. We can do another one, and this is a simply supported beam, and if you look closely, it's a little bit cluttered here, but all I'm doing is I'm applying a moment at the left end, concentrated moment at the left end. That's the only loading on this simply supported beam. The B support is here, and my goal is to get the deflection at C. Well, C is out here, and what do we know? Well, this portion of the beam has no loading on it, so we know that that it's going to be straight. It will remain straight. So when I apply this bending moment like this is going to deform like that, and then it's going to be a straight line from B to C. So as we said, what we're going to do is we are going to analyze this portion of the beam, and then we are going to find the slope at that point, and then we're just going to use geometry to extend that straight line. Again, what do we have to do? Find the reactions, draw the shear and bending moment diagrams. I'm not going to go through that. But here are my reactions. I draw my shear diagram down to over up to. I have my concentrated moment of 10, so we're up to 10, that area is negative 10, I go down to 0. And then of course what we see is that there's no shear, there's no bending. That means that that portion of the beam does not deform, it's a straight line. So from BC, it's a straight line due to the fact there's no shear, no bending moment. I know that the slope is negative 2 here, so I can begin by writing my equations. I really don't need to write an equation for V, it's too simple. Now I'm just going to immediately write the equation for the moment diagram. I know the slope is negative 2 because the shear is negative 2. And I know the intercept is 10. So the equation of that line is negative 2x plus 10. I'm now going to integrate it twice. So the first time I integrate it, I'm integrating negative 2x plus 10. I get negative x squared plus 10x plus c1. I integrate this, and I get, well, I end up with c1x plus c2 and all the other. I have to put in my boundary conditions. It's a simply supported beam. So what do I see? I know that the deformation looks like this. So I get deflection of 0 at B, deflection of 0 at A. So that just means that the deflection is 0 at those 2 points. So I have my boundary conditions at x equals 0, y equals 0, and at x equals 5, y equals 0. So I take at x equals 0, y equals 0, I can put that into here, and I get that 0 is equal to 1 over EI times 0 plus 0 plus 0 plus C2. That tells me that C2 is equal to 0. And then I use the other one at x equals 5, y equals 0, and I get that 0 is equal to 1 over EI times, now I'm putting in 5, negative 0.333 times 5 cubed, plus 5 times 5 squared, plus C1 times 5. I solve for C1, I get negative 16.7. So my equation for dy dx is 1 over EI times negative x squared plus 10x minus 16.7 because I have the C1. And what I'm trying to figure out to do this particular problem is I want the value of the slope, the value of dy dx, when x equals 5, because that was the question. Or that's what's going to help us solve this. Remember, we have to get the slope at this point because we're just going to extend that upward to get the deflection at C. We wanted the deflection at C. That was our goal. So plugging everything in, I get dy dx at x equals 5 is 0.00415. And notice that's a slope, not an angle. So it's a slope, and what we're going to do is we're going to create this triangle here. We have similar triangles. I've got the inner triangle, which shows the slope. I have the outer triangle for my beam. And what do I see? If I look at those two similar triangles, I get that yc over 0.00415 is equal to 2 over 1. And I can solve for yc, and yc becomes 0.0083. And we got our answer. I want to look at, so I'll take this one step farther. I want to look at the same beam, and I want to find what is the maximum downward deflection. So same problem, we've already solved for the equations. And what I want to do is I want to find the location where dy dx equals 0 in the region between x equals 0 and x equals 5. In other words, we don't know. We know that the deflection of this beam is going to look like this, but intuitively we can say that the deflection is not going to be maximum at the center because I have my concentrated moment at the left side. So, I mean, you don't have to use your intuition, but you should try to, develop some intuition and understand that what's going to happen is this is going to bend down more toward the left, and then it's going to curve upward like that. So all we need to do then is to look at our dy dx equation, which is that, and I want to determine when dy dx equals 0. So I'm just going to set it equal to 0, and then I'm going to solve for my value of x. And of course, it's a quadratic equation, so you can either do this on your calculator or use the quadratic formula. If we plug everything in using that a is -1, b is 10, c is -16.7, plugging it in, I get two answers, 2.19119 meters or 7.9 meters. It's not that one because that's out of our range. So we get x equals 2.119 meters. Then what do? I need to plug that into the equation for y. We develop the equation for y, and I simply plug this value of x into it, and multiplying it all out, we get y is equal to -0.00805 meters. And again, notice that this 2.119 is not halfway. Halfway is 2.5. So our intuition was right that the bending is going to look more pronounced at the left side. We get more deflection at the left side of this beam. All right, I'll do this next time.